This is the aged river control system, an unassuming array of floodgates and levees situated in central Louisiana along the Mississippi River. Constructed during the 1950s, it aimed to address a significant issue. Normally, rivers solely converge, with tributaries merging and blending as they flow downstream. However, the Mississippi River deviates from this norm, possessing a distinct point where it splits into a secondary channel known as the Atchafalaya. The Army Corps of Engineers knew that if they didn't act fast, a huge portion of America's most significant river might change its path entirely. So they built the old river control structure, which is basically a dam between the Mississippi and Atchafalaya rivers, with gates that control how much water flows into each channel on the way to the Gulf of Mexico. It was certainly an impressive feat, and now millions of people and billions of economic dollars rely on the stability created by the project. The now static nature of the Mississippi River that once meandered widely across the landscape. That's why Dr. Jeff Masters called it America's Achilles heel in his excellent three-part blog on the structure. The Atchafalaya River is closer to the Gulf and has a steeper slope. If it failed like it almost did in 1973, the Mississippi would divert, stopping freight traffic, depriving New Orleans of water, and causing an economic crisis worse than the Suez Canal blockage. Mark Twain famously said that 10,000 river commissioners, with all the minds of the world at their back, cannot tame that lawless stream, cannot curb it or confine it, cannot say to it, go here or go there and make it obey. And engineers have spent the better part of the last 140 years trying to prove them wrong. Now we want to show you some examples of where humans try to control Mother Nature's rivers and why those attempts often fail, or at least cause some unanticipated consequences. We've teamed up with a river maker of these awesome stream tables to show you how this works in real life. One of the most disruptive things that humans do to rivers is build dams across them, creating reservoirs that can be kept empty in anticipation of a flood or be used to store water for irrigation and municipal supplies. Rivers transport not only water but also sediment. Similar to a dam that holds water, rivers act as reservoirs for the silt, sand, and gravel they carry. This is evident in the flow model of a dam. Swift water can carry more suspended sediment compared to slower water. As the water enters the pool, its velocity decreases, leading to the settling of sediment. Gradually, the sediment accumulates within the reservoir, giving rise to significant problems. Firstly, the reservoir's capacity diminishes over time due to the accumulation of silt and sand, rendering it less functional. Water leaving on the other side of the dam, whether through a spillway or all the works, is mostly sediment-free, giving it more capability to cause erosion to the channel downstream. But there's a third impact, maybe more important than the other two, that happens well away from the reservoir itself. Can you guess what it is? This diagram, called Lane's balance, simplifies the behavior of rivers into 4 parameters: sediment, volume, sediment size, channel flow, and channel slope. You can see when we reduce the volume of sediment in a stream like we would by building a dam, Lane's balance dips out of equilibrium into an erosive condition. In fact, according to Lane's balance, anytime we change any of these 4 factors, it has a consequence on the rest of the river, as the other 3 factors adjust to bring the stream back into equilibrium through erosion or deposition of sediments. And we humans make a lot of changes to rivers. We want them to stay in one place to allow for transportation and avoid encroaching on property. We want them to drain efficiently so we don't get floods. We want them to be straight so that the land on either side has a clean border. We want to cross over them with embankments, utilities, electrical lines, and bridges. We want to use them for power and for water supply. But as we'll see with the help of this awesome demonstration that can simulate river responses, they often come at a cost. And sometimes that cost is borne by someone or someplace much further upstream or downstream than from where the changes actually take place. A classic example of this is stream channel straightening. In urban areas, we frequently untangle waterways to expedite water flow, minimize flood effects, and impose a more orderly path on meandering rivers to optimize space utilization. I can demonstrate this on the stream table by cutting a direct line that bypasses the natural bends of the river. The consequence of straightening a river is a shorter channel length, resulting in an inevitable increase in its slope. A steeper channel accelerates water flow, intensifying its erosive power. So the practical result of straightening a channel is that it scours and cuts down over time. It's easy to see the results in the model. This is compounded by the fact that cities have lots of impermeable surfaces that send greater volumes of runoff into streams and rivers.